Today I would like to talk about chapter 13 of gas dynamics, is devoted to numerical techniques for supersonic flow. We have discussion about two main topics. They are method of characteristics, classical computational method, which leads us to supersonic nozzle design, profiling of supersonic nozzle. And second method, which is a finite difference method, which is modern CFD computation today. These two methods are totally different because they involve different computational models and different approaches, but they have also something in common. This is why they are inside the same chapter, chapter 13. We also discuss difference between stationary simulation and transient simulation for subsonic, supersonic flows. And we discuss some results of simulation of flow over supersonic blunt paths, re-entry capsules, and some bodies which create ball-type shock waves. Numerical approach. So these two methods, which are method of characteristics and method of computational fluid dynamics, they are all numerical methods based on transformation of a continuous dimension or continuous space into discrete points, grid points. In the case of characteristic mesh, such grid will be a result of calculation. We don't know this grid from first moment of calculation. So characteristic lines or grid lines and grid points and parameters on cross-section of these characteristic lines will be calculated during a process of solution of equations. And a mesh for CFD calculation, as you know from aerodynamics, is built before starting any simulation. This is the main difference between two types of meshes. One mesh we receive during calculation, second mesh we calculate before starting simulation. In details, we will talk very soon. First of all, we talk about method of characteristics. What is method of characteristics? Is an attempt to solve equation 12, which is a classical equation of potential for compressible flow. This equation we already saw in chapter 11. Actually, this equation has number 11.12, so it means this obtained in chapter 11, and it describes distribution of potential function in side compressible flow. Here in this equation, together with the potential function phi, we have also definition of speed of sound. This equation can be transformed, can be rewritten once we regroup it near second derivative on xy direction. And the mixed derivative, we can rewrite it using approach of mixed derivative presented in equation 13.2 and 13.3. And as a result, we obtain this equation, or similar equation to what you see on 13.1. This equation has second derivative of potential function on x direction, on y direction, at mixed derivative d to f by dx dy, mixed derivative of second order. As we know, this equation is not linear, so it cannot be solved analytically. So what is the approach to solve this equation and how to elaborate method of characteristics? This is a tricky approach, purely mathematical, based on the following. We can transform or we can calculate this equation, solving it for mixed derivative. So we can rewrite second derivative of potential function as you might see on equation 13.2. Okay, we write this differential du, which would be equal to second derivative of potential function on x multiplied by dx plus second derivative of potential function by dx and dy multiplied by dy. Same way we proceed the calculating differential of dv. What is important that in equation 2 and 3 we have second derivative which can be applied in equation 1 inside this equation here. Once we substitute second derivative from equation 2 and 3 inside the equation 1, we obtain equation 1 in terms of just mixed derivative. It would be just a function. Equation 13.1 would be a function of d2f by dx dy. Okay, and would not be any second derivative, purely second derivative of x and purely second derivative of y direction. Then this equation we can solve and obtain what would be this mixed derivative. This mixed derivative is represented on equation 4, is a ratio between determinant of matrix because it's sorry, I need to turn off my cell phone. So we can see that second or mixed derivative on dx dy would be a ratio of matrices or determinants. Right? We can do it by hand or we can do it with computer. And now we see that potential function will depend on several parameters, on velocity, on u and v components of velocity, on speed of sound, and differential on x direction, differential on y direction, and differential on velocity, both in numerator and denominator. And now, instead of solving this equation, we will see some specific properties of this equation. So these specific properties is shown here on the lower right corner. We will search at which conditions this mixed derivative is indeterminate, or numerator and denominator of this ratio would be equal to 0. Both of them would be equal to 0. It's not exactly solution of equation 4 or not exactly solution of equation 1, but the mathematical approach to solve such equation is to find these special conditions at which mixed derivative is indeterminate. Why it's done is another question. It doesn't have any relation to physical process, but it has some mathematical background which is outside of our current discussion. So we will search at which conditions numerator and denominator of formula 4 would be equal to 0. First of all, we will work with the numerator. How we find determinant of this matrix, I hope it's quite clear. There is an analytical formula to find a determinant of numerator of ratio 4. Here it is represented inside the equation 6. This matrix equal to 0. And we can see that we can group equation 6 near second order of dy by dx and the first order of dy by dx, and here 0 order of dy by dx, which is not present, which is equal 1. Okay. this one is 0 order of dy by dx. This dy by dx is some direction we would like to know. This direction, which exactly corresponds to indeterminate value of mixed derivative. And since it's a square equation, equation 6 is square equation, we can solve this equation inside the by known method of solving square equations. And we can represent this solution in equation 7. So some direction, the dy by dx, which corresponds to our equation of potential, would be an analytical solution represented in equation 7. It's a ratio between velocity product and square root of speed of sound. It will be also some proportion between velocities. Right? There are no other parameters than velocities. And when we know this solution, we can make we can substitute this solution by representing u and v component of velocity as function of angle of inclination of flow and the main component of velocity. I will try to make a small drawing here. When we have velocity vector, right? U component of velocity and the v component of velocity theta between them. So we can see that u component of velocity would be v cosine theta and v would be v sine theta. So this transformation gives us relation between velocity components and velocity module and direction of velocity. We substitute these formulas in equation 7 and we obtain equation 8. Then, knowing that there is a relation between Mach number and speed of sound, I think. Let me see, before we had this formula and it was in the previous chapter that sine of or arc sine of Mach angle was a ratio between 1 divided by m, right? 1 divided by m. And we apply this formula in equation 8, we obtain equation 9. Instead of Mach number, which you can see here when we analyze this equation, velocity divided by speed of sound. This is purely once we join this ratio, it will be Mach number in square, right? Same we have here, Mach number in square, and same we have here, Mach number in square. And rewriting instead of Mach number, Mach angle, mu, which is related to Mach number, we obtain equation 9. 13.9, we see that instead of Mach number, we have sine of Mach angle. And so m in square is equal to sine of Mach number in square, right? Yeah, it looks like, or no, 1 divided by sine, sorry, 1 divided by sine because it's opposite. Then we can simplify this equation by known trigonometric functions. Instead of sine, we obtain tangent and simplifying just applying knowing transformations, mathematical transformations from equation 9, we obtain equation 13.10, which is saying to us that dy by dx, which is direction of some line on which we are searching this solution, would be equal to tangent of theta plus or minus plus mu. Theta, which is direction of flow, and mu, Mach angle. Here we can see one word char is characteristic, is the direction which we are looking of this line would be called characteristic line, or line of characteristics, and dy by dx is the slope or direction of this characteristic line. You can see line in space, and at any particular point we would have this dy by dx direction, which would be related to direction of flow or tangent of direction of flow theta and angle of Mach. Since there is sign minus plus mu, we know that there are two characteristic lines, so not just one, but there are two characteristic lines which would be directed according to flow direction plus minus direction of Mach angle. Here is the picture representing such a concept. Please let me know by voice if you have some questions today, because I have my other computer broken and I cannot see if there are comments or there are no comments. So if you have some questions, please let me know by voice today. Some technical problem. Here is representation of solution or formula we obtained before. Maybe I would just show both on one screen and remove my picture from here. So there is an arbitrary point A in space at which we have direction of flow theta known. This theta is angle between horizontal direction and the velocity vector. Horizontal direction is just a sign convention. We can use direction between vertical axis, but then would be 90 degrees minus theta. So, but absolutely no problem, no difference which would be our reference. It just will change a bit the argument of function. So theta is angle of flow, or we had it in aerodynamics called angle of attack, but now it's angle of flow, right? And there is mu. We can see this mu between vector of velocity and characteristic line in a positive direction, and also there is same, oh sorry, not very aligned with characteristic line, and with the negative direction. Mu plus mu and minus mu according to equation 10. So at each at any specific point A, we can find two lines going in two different directions according to flow direction and according to Mach number, according to Mach angle. Mach angle and Mach number are related. So these are directions of characteristic lines. Here on figure 4, we can see that characteristic lines, they have names, C plus and C minus. C plus is called left running characteristic line. Now, why is left? Because if we are looking to direction of, this is our eye, we are looking to direction of flow, C plus would be on the left from our eye, so it's called left running characteristic line. And the C minus, another characteristic line, would be on the right. It's called right running characteristic line, C minus. So both these lines have names. C plus is where we have inside tangent function theta plus mu, and C minus is where inside the tangent formula, previous one, 10, I think, right? It was 10. We have theta minus mu inside the argument. This is happening for any particular point in space. Since in each separate point we have or different direction of flow or different Mach number, we know it can change according to, for example, asymptotic flow relations. We can find Mach number changing inside the nozzle or inside the asymptotic diffuser. Inside the asymptotic flow, parameters usually change when they are close to a physical body. So at each point would be different theta, and at each point would be different Mach number. It means that direction of characteristic line would be also different at each point. This is why line C plus and C minus, they are curved. They are not straight lines. In many cases, for example, in calculation of nozzles in method of characteristics, we assume that characteristic lines are straight between points. This is simplification, allowing us to use linear law or linear function of characteristic line direction. But we always keep in mind that real characteristic line will not be straight, it will be curved. Since distance of calculation in our space would be considered as very small, we consider that approximating my notes are close, sometimes it happens. Approximation between points linear is acceptable because distance between lines is very small. I did not discover yet why sometimes program of notes is closing, but I think it's internal problem of software. Already open. Okay, we are back. Please let me know if you can hear and if you can see my screen again.
Yes, it's working.
Okay, thanks. So dn is a small distance between points. We approximate characteristic line as a straight line. Okay, and then going to another point would be another straight line, and etc. So when this happens in a small space, points are close one to another, error of calculation would not be big. But in case when we have very few points, so points are distant from one from another, of course, we will have some considerable error. As usual, for typical for any numerical methods, we know that if we use many points in calculation, it would be more accurate. If we use just a few points, it would be less accurate. Number of points we choose according to accuracy and available time. Accuracy we would like to have and available time we have for calculation. So this was a result of calculation of just numerator of this mixed derivative. I remind you that we are trying to find solution where mixed derivative of potential function would be undeterminate. Numerator gave us direction of this line at which solution would be undeterminate. Now denominator we analyze. Now we will analyze numerator in the same way we saw it's a matrix of 3 by 3 and determinant of this matrix can be calculated easily. Such calculation you can see on first equation on your screen. We see that equation is simpler, right? Because matrix is having more zero values inside. And as a result, analyzing this equation, you can divide by dx and by dy, by du and by dx. And we obtain on the left side, transforming first equation, we obtain the second one. On the left side, we will have dv by du. ratio of differentials of velocity in v and u direction, on y and x direction. And on the right side of this equation, we have ratio between velocities and the ratio between dy and dx. This dy and dx, which we previously already received in first analyzing first relation numerator of our ratio. Now we make same transformation of velocities from v and u component of velocity. We transform it to a module of velocity v and the direction of velocity theta in numerator and denominator here. And on the right side, we, instead of using velocity ratio and to speed of sound, we use definition of Mach number, and also we make this transformation to module of velocity and velocity direction. So we receive right side of equation transformed here. This equation, you can see intermediate one. It can be simplified, and this simplified version is shown on equation 14, or simplified equation 11 is equation 14. There are several equations missing in this logic. If someone wants, can go and see how transformations are done from equation 11 to equation 14. But it's just mathematical relation, just mathematical transformation. So we obtain relation between differential of direction of flow, d theta, as the function of Mach number, and ratio between differential of velocity and velocity value. This equation we already saw previously in the previous chapter. I would like to remind you that this is absolutely same equation, which is called Prandtl-Meyer equation. So this equation has analytical solution. It can be integrated on the left and right side, and we can find analytical solution of this equation. One aspect of this equation 14 is that there are actually two equations. Each one corresponds to each characteristic line. Since we have two characteristic lines at each point, negative and positive, or left running and right running characteristic line, we have also two solutions of Prandtl-Meyer flow. We have solution for C- line, which you can see on equation 15, which is d theta is equal to minus of m square minus 1 square root multiplied by dv by v. And for C plus, it will be, for the left running characteristic line, d theta would be square root of m square minus 1 multiplied by dv by v ratio. For each of these equations, 15 and 16, we can find the solution according to Prandtl-Meyer solution. And integrating, we will see equation 17 as solution of equation 15, right? Yeah. Equation 17 saying to us that direction of the flow theta plus Prandtl-Meyer function m would be constant, and would be this constant would be named k minus some constant which would be same along the characteristic line. And on the characteristic line C plus, we have very similar definition, but with a different sign. We will see that difference between direction of flow and Prandtl-Meyer function along the line will be also constant and would be equal to k plus. how it can be calculated in practice. What does it give to us in practice? Let's imagine that we have a line already defined on previous equation. This equation we had right here, equation 10. So we know the direction of some characteristic line on the flow. It will be not line, streamline, nothing like this. It will be some line in space which goes starting from point where we can calculate. Oh, let me put in the middle because probably this line came from somewhere. So this is our point A in space. We have one line and we have another line, two characteristic lines on the same point. Let's take, okay, this C plus is on the top, I think, right? They are called C plus, just, yeah, is on the top where we summate direction of flow and math. So this is C plus and this is C minus here. For example, we know parameters at point A. So we know theta and we know Mach number at point A. Using this function 17, we can calculate constant K minus or K plus, no matter. They will be same, no, they will be different, sorry, they will be different. And this constant would be same along the line, anywhere along the line would be same value of this constant. So once we know direction of the line and we have point B on this line, what we can have relation between direction of flow and the Mach number at point B. If we know one, we know the other. If we know, for example, where flow goes at some particular point B, we will know what would be Mach number at this particular point B. How we can know this? For example, I take on a C plus. I take on C plus. Let's have one simple calculation. We have space for this calculation. Let's assume that, okay, this would be negative direction of flow. Let's assume that my theta is, it's not a mistake, minus 10 degrees and at point A. And my Mach number is 2, also at point A. I need to know the Prandtl-Meyer function at this point A as a function of Mach number. I will need to go to appendix C, probably, right, and calculate. Just a moment, I will open this appendix. I will try to open this appendix because it's on the same computer. Okay, for Mach 2, it will be 2638. 2638. Okay, degrees. And now, for example, Okay, we had theta negative minus 10 degrees. For example, at point P, we have 0 theta. Theta at point B is equal 0. And what is missing to calculate this constant? I would have my constant K plus at point A would be, oh, no, sorry, not K plus, it's K minus. K minus at point A, because it goes down, would be minus 10 plus 26. Okay, I just would like to use 26 degrees because 38 becomes too long. Plus 26, it will be 16 degrees, right? Please let me know if I make some mistake, some simple mistake, I would correct immediately. 16 degrees. And if I have 0 degrees at point B, my K minus is same, is minus 16. Oh, sorry, plus 16 degrees, because I'm still on the same characteristic line at point A and at point B. And it will be also theta plus nu of m at point B. Theta in our case is 0, so nu at point B, okay, is a function of Mach number at point B is 16 degrees. So let's see what would be the value. I'm looking in Appendix C, value of Prandtl-Meyer function close to 16 degrees, and I find that this Prandtl-Meyer function corresponds to Mach 1.64 approximately. 164 is the Mach number at point B. Okay, this is the calculation. So when I know direction of characteristic line, and I know it because I already knew values of theta and Mach at point A, I know where point B would be exactly. And if I know direction of the flow at point B, I will calculate Mach number at point B. Okay. That's it. In a similar way, we can calculate if we do not know direction, but we know Mach number at some specific point. Let's have also this simple example. For example, I have a point C on the top, so it's C plus characteristic line. So for C plus characteristic line, K plus would be theta minus nu, and it will be minus 10 minus 26 degrees, would be minus 36 degrees. And if I know that Mach number at point C, how much would be? 2.5, for example. 2.5. Prandtl-Meyer function at point C would be, let me check, 39 degrees. And I know that there is a relation, right? The relation says to us that this K plus, which we calculated, okay, I will use here the previous one, previous line, would be theta at point C minus Prandtl-Meyer function, sorry, at point C. And since I know this 39 degrees would be theta minus 39 degrees. From here, how much would be the theta? Probably it's plus, right, plus 3. So if Mach number is 2.5, at point C, we know that direction of flow would be plus 3 degrees. I hope my calculation is correct. If there is some error, please let me know by comments saying this. Okay, so we need to know one or the other. We need to know or direction of the flow or Mach number. But what if we do not have? What if we are in space between point A and point B? There is no relation. Okay, no, we don't know neither direction of flow nor Mach number. What we need to do in this case? In this case, we need to build a mesh of characteristic lines. And since characteristic lines intersect, at point of intersection, values of flow properties would be absolutely same for left running and for right running characteristic line. For example, at point A, for both characteristic lines, Mach number and direction of flow would be absolutely same. Of course, K minus and K plus are different, but flow properties are same. So we need the two lines intersecting. And because of this, we have two different cases. We have case one, which is called internal points, where two lines are intersecting inside flow. And case two would be wall points, where two streamlines are intersecting on the wall. Direction of the wall is same as direction of the flow near the wall. So we know the direction of flow on the wall. So let's talk about internal points. Once we see two intersecting characteristic lines starting from point 1 and point 2, we know their properties. We know properties because point 1 and point 2 are starting points for calculation. So we can calculate K minus and K plus according to our previous formulas. We know theta 1 and nu 1 from initial conditions, and we know nu 2 and theta 2 also from initial conditions. So these are initial points 1 and 2. And we know the direction of characteristic lines because we know Mach angle, we know theta. We can build what is the direction of characteristic line starting from point 1, how exactly it goes, and starting from point 2, how exactly it goes. Once we know these two lines from point 1 and 2, and they are not parallel, they will never be parallel probably, because to different points it's hard to have parallel lines mathematically, almost impossible. And they will always intersect, and probably they will intersect very soon at point 3. At this point 3, we will have theta and nu same for both lines. Combining equations 19 and finding solution between these two characteristic lines, we will see that direction of flow between two intersecting characteristic lines would be average between values or constants on characteristic lines. I say average because it's constant 1 plus constant 2 divided by 2, so it's mathematical average. And the Prandtl-Meyer function at point of intersection of characteristic lines would be a half of difference. We have 1/2 of characteristic line negative minus characteristic line positive. We have theta at a point of intersection, and we have a new point of intersections. Once we know this, we can obtain Mach number. You can see here a small schematic how calculation can be done. Item 1 is knowing Prandtl-Meyer function. We obtain Mach number from Appendix C. After item 2, from Mach number and knowing stagnation properties, pressure and temperature, we can obtain parameters of pressure and temperature, for example, and also density by equation of state. Don't forget, the equation of state works at any conditions for compressible, incompressible, viscous, inviscid, asymptotic, not azeotropic, absolutely any type of flow. So density is absolutely not a problem when we know pressure and temperature. And we know gas composition, of course. We know gas constant R and gamma. Then knowing temperature, we obtain by item 3 formula speed of sound, A3. And then velocity 3 is a product of Mach number calculated before at item 1 and the speed of sound. We obtain V, then we can obtain velocity components once we split this velocity and we know theta, right? We go to calculate U and V components of velocity. So we know all direction of flow, we know pressure, temperature, density, practically all, right? And the main assumption is that stagnation properties are constant, so flow is asymptotic. One limitation which I did not explain you at the very beginning of talking about method of characteristics, that it can be used only for supersonic flow and it can be used only for isentropic flow. So we do not have losses and flow is always supersonic. Method of characteristics cannot be used for subsonic flow because Prandtl-Meyer function does not exist for subsonic flow and Mach angle mu also does not exist for subsonic flow. This is why only supersonic and only isentropic. If we have losses, this method doesn't work. I hope it's clear. Second case is wall points. Wall points is simpler because on the wall we always know direction of the flow, as I told you already. For example, here, figure 6, showing to us this case. Starting from point 4, at which we knew flow properties, we go to point 5. Point 5 is intersection between characteristic line and the wall. These two lines will always intersect because characteristic line can never be parallel to the wall, at least here, right? It will intersect at point 5, and at this point 5 we always know flow direction, theta 5. Theta 5 is the same as wall direction, because vector of flow or direction of flow is parallel or tangential to the wall. So theta 5 is known. K minus 5 we calculate starting from point 4. K minus 4 and K minus 5 are same because they are placed on the same line. They stay on the same line and is equal to theta 4 plus nu 4. Direction of flow plus Prandtl-Meyer function at point 4. Since we know all parameters at point 4, we can calculate this constant. And at point 5, the only unknown is Prandtl-Meyer function. Can be easily calculated from equation 26. At point 5, we will know how much is Prandtl-Meyer function as a consequence presented on my previous slide. We know what will be Mach 5, what would be pressure 5, temperature 5, and all other parameters like speed of sound, velocity, velocity components. So wall points are easier to calculate once we start from known point at 0.5. No system anymore, just straight calculation. Please let me know if it's more or less clear. If you have some questions. And I would like to present you how in practice can be used this concept of characteristic lines. Another comment I would like to give you before explaining the calculation presented on figure 7 is that the model we discussed is the simplest possible model, is always applied to two-dimensional planar nozzle, which you can see on the top of this slide. It means that nozzle is not a body of rotation, is just a planar two-dimensional nozzle with the third dimension going to infinite. Okay. If you would like to calculate a nozzle or axisymmetric rotational body, you need to use a similar model, but for axisymmetric flows. Why is not present on the book is another question you may ask. The answer is simple, that instead of solving just algebraic equations for Prandtl-Meyer function and characteristic line direction, we need to use for characteristic line direction, instead of algebraic equation, we need to solve differential equation at each point. And from didactic point of view, it becomes heavier and not possible to visualize and to show by simple Prandtl-Meyer function Mach angle relation. The direction of characteristic line would be calculated from ordinary differential equation. It is not difficult. It is relatively simple. Anyone can do it if you read the book of, let's say, all publications devoted to method of characteristic for axisymmetric flows, but it is not included in classical theory we study here in gas dynamics. If some of you would be interested to implement in your programs this method of characteristics, please let me know. In general, it's not very difficult, and I believe any of you could provide such calculation when needed. So this is my comment about applicability of method of characteristics presented in the book. In general, we can see two different methods of characteristic. This one, more simpler for just two-dimensional planar flow to understand how method is working, and more complex for axisymmetric nozzles, which could be applied for real nozzle applications, right? Because mostly all nozzles are rotational axisymmetric bodies. But planar nozzles also are present in aerospace structures. There are several engines working in such geometry, planar nozzles. They are having some advantages with respect to axisymmetric nozzles when we have a limited thickness of a body. For example, it should be installed on the airplane, low profile airplane, then planar nozzles, or let's say, planar nozzles can be better option than axisymmetric rotational nozzles. Calculation presented on figure 7 is done the following way. Actually, Anderson explains a lot how this calculation is done point by point. I give you an idea, and I will not calculate for you here because of two reasons. It's already explained in the book, and second, I already recorded video about this calculation. You can see on the questionnaire of gas dynamics. I give several examples how to calculate this nozzle by method of characteristics. So this was already presented, but idea I would like to explain. The idea is following. We have a sonic line, which is presented on figure 7. Sonic line is the line on which Mach number from subsonic starts to be supersonic after this line. So on the sonic line, Mach number is equal 1. We see that 0.1 and 0.2 are starting points for our calculation are placed after sonic line. So at 0.1 and 0.2, Mach number is supersonic, m more than 1 at 0.1 and at 0.2. Consequently, as I told you, method of characteristic is limited by supersonic flows. It cannot be used for subsonic flow calculations. So 0.1 and 0.2 should be inside supersonic flow. Let's assume by some method, by empirical estimations or by numerical simulation, we can obtain Mach number at 0.1 and 0.2. What happens next? We know that at 0.1, flow is same as direction of the nozzle, and since nozzle is having exactly horizontal direction, we know theta. At 0.2, we also need to know overall flow properties, theta, direction of flow, and the Mach number. We also can assume in, I think, in most cases that direction of flow at 0.2 is also having zero inclination. It's parallel. It's parallel. On the axis, of course, 0 theta. On the wall is also 0 theta. So it would be obviously to assume that between these 2 points, flow direction would be also horizontal. Okay. Okay. The size of vector which I draw you here does not exactly represent the value of velocity, just represents direction of velocity. How much would be values at 0.1 and 0.2 will depend a lot on geometry of the nozzle. We cannot say that Mach 1 will be bigger than Mach 2 or Mach 2 would be bigger than Mach 1 definitively. Unfortunately, I saw cases where Mach 1 is bigger than Mach 2, Mach 2 is bigger than Mach 1, or some cases at which they are equal. It's less likely because we have geometry changing of the nozzle. So probably one or the first or second Mach number would be bigger, another would be smaller, but it will not impact generally on calculation of the nozzle. We can assume small supersonic velocities, even already small, like 1.1, 1.2 Mach already allows us to use method of characteristics. From 0.1, we calculate characteristic line until, okay, it will be not until 0.4, it will be until the axis, it will be a straight line, okay, direct, straight, but at the first moment, we will know just direction between 0.1 and 0.4. We don't know where 0.4 is. 0.2, we choose in any arbitrary position, can be point in the middle between axis and wall, can be more closer to axis, more closer to wall, or even we could choose several points starting conditions. It would be more accurate to choose more points. We always have freedom to choose number of points for calculation. More points, more accuracy. In case of this example, we have very few points just for demonstration. In real calculation by method of characteristics, you can see tens or hundreds of points. So if we draw it, all these points here, it will be full of lines and full of points, would be absolutely unclear. This is why only for demonstration, there are very few points on this nozzle. For real calculation, we need many points on the nozzle. From point 1, we calculate characteristic line direction because we know Mach number and theta. Same we do for line 2. We calculate also characteristic line because we know direction of flow and Mach number. At some point, since we know direction, so we know inclination of this characteristic line started from point 2, we will know exactly where it intersects with the axis. And at the axis, we can calculate flow properties. We can, because we know that for any axial point, theta would be equal to 0 degrees. So we use case of wall points. Just fast, I return back to wall points and I show you that. Let's assume we had the characteristic point started at point 2. So K minus at point 2 was same as K minus at point 3 and was same as theta at point 2 plus nu at point 2. All these parameters we know. So we know K minus 2 and K minus 3. And after second equation, I will remove here all my notes and I will write you that since I know K minus at point 3 and I know that theta at point 3 would be 0, so 0 plus nu at point 3. From here, I know that my nu at point 3 would be exactly equal to K minus at point 3. And I already calculated before this Nonlinear function. And from here, I will calculate Mach number and point 3 and the rest of parameters. So point 3, we know how to calculate. When we calculate these parameters at point 3, we calculate left running characteristic line from point 3. Just a moment, I will choose another color. Starting from point 3, we will have this line, which I mark by red color or pink color. Point 3 or line starting from point 3, left running one, will intersect with line started from point 1. And we will know exactly where it happens because we have direction of both lines and geometrical position of both point 3 and point 1. We know where exactly in space point 4 will happen. And exactly at this point, we will apply system represented in part of internal points, this case here. So we will be capable to calculate direction at point 4 and Nonlinear function, and as a result, all other parameters at point 4. And starting from this point 4, we will calculate again two lines. I will change color again, and I will show you from point 4, we will launch right running characteristic line until axis, and it will give us 0.6. And starting from point 4, I will run a left running characteristic line, and it will give us 0.5 when it intersects with the wall of my nozzle. And in the same way, we will calculate all other points. I would like to change color again. From point 6, I will see, oh, sorry. From point 6, I will know how my characteristic line will go on the left side. And from point 5, I will know how my characteristic line will go on the right side. Where they will intersect, I will find my 0.7 in space. In the same inside the internal point, I will use system of equations to calculate flow direction and Mach number. From 0.7, I will start also 2 lines until point 8, until it will intersect my wall of the nozzle, and until point 10, until it will intersect my axis. Using concept of wall points, I will calculate parameters, flow parameters at point 8, 10, and in this way, I will continue to continue making my calculation until I go outside of the nozzle. So this is the way how calculation by method of characteristics can be done on the nozzle. If you would like to see solution with numbers, please go to one of videos of questionnaire of gas dynamics where I show how the solution is obtained numerically, point by point. I show several points, I think, not all, not until point 13, because it's useless. All operations are repeated one by one, and this algorithm can be easily programmed inside the computer, MATLAB code, or any other software, even Microsoft Excel can give us calculation of flow by method of characteristics. Method of characteristics is good not just for this calculation of points on the wall or inside the flow, but method of characteristics is also used to profile the nozzle. To profile, not just to obtain flow properties. How profiling of nozzle can be done? What is the idea? The idea is simple, that profile of the nozzle should be built in a way that it will not generate any change of entropy, or it will not produce any shock waves. So we have to preserve isentropic flow structure inside the nozzle, and in such a way we will obtain shape of nozzle. Mathematically, it means that, for example, looking on our picture here, it means that point near the wall of the nozzle and point on the nozzle would not have change of flow direction. So flow direction at points near the wall and points on the wall would be having same direction. So if two flows have same direction, they cannot produce shock wave, because shock wave appears only when there is change of flow direction or sudden change of flow direction. For example, we assume that point 7 and point 8 are close to another. Point 7 we calculate before calculating point 8. So point 7, having this point 7, I will have theta 7 and I will have m7. When I go to calculate point 8, I will assume that my angle of flow would be same for point 8 here. So I will write that theta 8 is equal theta 7. It's my conditions on the wall. And from here, I will calculate Mach number, my Mach number 8. You will see that since two parameters are same of angle, it will also result in the same Mach number of M7 and M8. In such a way, we have equilibrium of flow direction, we have equilibrium of Mach number, and we have no reason to have a shock wave, right? Our assumption is that 0.7 and 8 are extremely close one to another. If these close are distant, like you see on this figure 7, of course, calculation cannot be considered as accurate, right? But when 0.7 and 8 are close enough, we assume that they are almost same point, and we can provide this equilibrium between flow direction and Mach number direction in such a way, calculating flow direction at 0.7, we already define flow direction at 0.8. I hope it was clear. If not, please look into the book. If it will be still not clear, please ask me. I will explain you again based on this book example. Okay, this is a calculation. Some initial parameters I wanted to show you for calculation, some examples. Here I compare nozzle, planar nozzle, schematic from figure 7 and simulation in ANSYS Fluent. I use this example just to demonstrate for you importance of boundary conditions. These boundary conditions, they are flow conditions at the first starting point, point 1 and point 2. And I also plot for my CFD simulation on the upper right figure. It is distribution of Mach number in radial direction for two different lines. I have one line which is exactly on the throat, black line, you can see, and the flow properties on the black line. Exactly on the throat, we can find that big part of flow velocity is subsonic, so we can not use this data. And if I move just from throat line 2 millimeters inside the nozzle, you can see significant change of Mach number. We see that I can use any point as my boundary conditions, point 1, point 2, and any other point. On the axis, it's Mach number very close to Mach 1. Okay. And on the wall, where is the wall? It's somewhere here. I think it's 8 millimeters. On the wall, Mach number is already 1.7, so it significantly changes. Even with this very small difference in space, just 2 millimeters, this distance between two lines, you can see how different becomes the flow parameters or Mach number values, how different they are. So by this picture, I would like to say that for my personal opinion, is not so much important at which point exactly you will start calculate at point exactly on the throat or at point just 2 millimeters after the throat. Since we have a huge variation of Mach number at very limited range, you can start with practically any value starting from 1 to 1.7 to have a linear approximation. Okay, just a moment. Have a linear approximation or to have some preliminary simulation to obtain this distribution of Mach number along the radial direction, or to just select some constant value, for example, in the middle, 1.2 or 1.4 for all points near the axis, and on the wall can use same value. Not so much important for the final calculation, for my personal opinion. Maybe you will find different. You will find and you will have different conclusions. So please let me know if you research and found something interesting in this calculation or something which attracted your attention. The CFD calculation I made, but it was only possible after a calculation of nozzle by method of characteristics. So we cannot provide CFD from nothing, right? We need to use method of characteristics to make profiling of nozzle, to find nozzle shape, and only after can make CFD. But same time, CFD can serve for us as a preliminary estimation of flow properties near the throat. So these two tasks can be correlated. Or the third case, we can guess some value of Mach number on the throat or distribution of flow properties on the throat, or can just simulate this region here to find Mach value distribution. And after calculate on by method of characteristics, several many cases, right? Profiling this nozzle and put in CFD method to validate this method of characteristics. You can see that, for example, here is entropic. We cannot see any shock waves in the part of supersonic expansion. We can see after shock waves, but this is because we have low pressure inside the nozzle, not because of nozzle shape. Right? Low pressure inside nozzle means very high expansion ratio or very low pressure inside combustion chamber, not related with shape, related with the relation between pressure in the nozzle and atmospheric pressure. Okay, please let me know if you have questions. I think that method or finite difference method I will give you next time. We still have time to discuss about it. Please read the book, and the next time I'm expecting also your questions, if they will be, would be nice, because method of characteristics is actually the only method we use for profiling of supersonic structures. Can be used not just for nozzle, but also for supersonic diffuser working at azentropic conditions, and for many interesting applications. I can wait 1 minute more until your questions. If you have some questions, let me know. I will switch to see if there are comments.
Professor,
please.
In terms of performance, which approach would be the best? Method of characteristics or other approaches such as parabolic approximations or others that exist for rocket nozzles?
Nice question. Parabolic approximation, as it follows from its name, is approximation, is how to say, a way to represent solution of method of characteristics in some simple function, in a parabolic function. So we use parabola to explain a complex flow concept. From point of view of time expenses, of course, parabolic approximation is easier and it's simple, right? Just use spline or just one parabolic function already will obtain nozzle profile. But the method of characteristic is more fundamental, because it uses equations of conservation, and parabolic function is just an approximation to this method, not exactly solving original equation system. Is same as, for example, we will how to say, we will measure some drag coefficient, for example, or we will calculate drag coefficient by CFD method, and we will use approximation of this drag coefficient from some experimental data, some empirical function. Is something similar, right? The result would be very same, could be same in several cases, or in many cases could be same. But the nature of these two methods are very different. One is analysis of previously solved flows, and the other one is exactly solution. I hope it's clear. For practical application, it depends. If you manage to work with the method of characteristics directly, it's always better, because you will not depend on one or another approximation of existing solutions. You can, if method of characteristic is working perfectly in your code, you will be sure that you are solving the flow. But parabolic method of parabolic functions, it's simple, easy, fast, right? So we always find the trade-off between time and accuracy, time and deepness of one or other involvement in calculation methods. Of course, we can use both of these methods, but I prefer most fundamental, which is method of characteristics. But if there is no time or there are not enough information about several aspects, could be also approximation. Both of these methods are worth to be considered. And sometimes it's even good to compare two methods, different methods.
Okay, thanks.
Okay, you're welcome. Please do not forget we have a third method, CFD simulation. You can simulate nozzle created by method of characteristics and nozzle created by parabolic functions and see if you will have losses, right? If you have some difference in the flow. It is also good to use viscous model, non-viscous flow simulation and viscous models. I think very soon when we go to talk about turbulence, we will touch this question, when it's worth to simulate viscous flows, because not always simulation of a viscous model will be giving significant difference. From time consumption, it's always more longer, but from result, it's not always worth to pay so much time for this small change or small difference. We will discuss it also soon. Please do not forget, validation is important. So any design of nozzle should be calculated not just by one method. It's good to use at least 2 methods or 3 methods, different approaches, and also validation by experiment is the best way to see if your calculation was correct. Okay, I see no more questions. Probably we can finish for today. I will stop my recording.